Assalamu alaikum, brothers and sisters. Welcome to the journey of quest where we quench your thirst of knowledge. Have you ever pondered over the question, what makes the Earth's crust move, crack, and deform? Welcome to an intriguing exploration of our planet's structure, a journey that takes us deep beneath the surface to the core of what makes Earth, Earth. We're setting the stage for an enlightening discourse on structural geology and geotectonics, the twin pillars that help us comprehend the very framework of our world. Consider this. The Earth is not a static entity. Just like a living organism, it evolves, adapts, and transforms. The unseen forces that drive these changes are as captivating as they are complex. Imagine the colossal plates that constitute Earth's crust, continually shifting and sliding over the underlying semi-fluid asthenosphere. This ceaseless activity, known as plate tectonics, is a prime mover in the grand saga of our planet's evolution. It's the force behind the creation and destruction of continents and oceans, the rise of mountain ranges, and the occurrence of earthquakes. But here's the thing, plate tectonics doesn't work in isolation. It's part of a larger process that involves the deformation of rocks under different conditions. When the forces acting on a rock exceed its internal strength, it fails, leading to fascinating geological phenomena like faults, folds, and joints. Understanding these processes is not mere academic curiosity. It's key to predicting natural disasters, exploring natural resources, and even planning our cities. Our knowledge of structural geology and geotectonics shapes our interaction with the Earth and influences decisions that impact millions of lives. As we embark on this journey, we'll delve into the mechanisms that cause rocks to fail and slide, unravel the mysteries of Earth's internal structure, and explore the influence of tectonic forces on our planet's crust. Now let's delve deeper into the fascinating world of structural geology and explore the different types of failure and sliding criteria. Imagine the Earth's crust as a giant jigsaw puzzle with its pieces constantly in motion. Now let's delve into the forces at work beneath our feet that keep this puzzle in perpetual motion. At the heart of it all are tectonic forces. These are the unseen hands that subtly and incessantly mold the Earth's crust. First up, we have compressional forces. Picture two of your hands pushing against each other. That's compression, a force that squeezes and shortens the crust, leading to the formation of features like mountains. Next in line are tensional forces. Imagine pulling a piece of taffy apart. This force stretches and lengthens the crust, creating rift valleys and ocean basins. Finally, we've got shear forces. Think of it like trying to slide two books past each other. This force causes the crust to deform by displacement along the plane of contact, resulting in horizontal deformation. But what's happening within the crust when these forces are at play? This brings us to the concept of stress and strain in geology. Stress is the force applied per unit area, while strain is the deformation that results from this stress. Stress can be likened to the push or pull exerted on the crust, and strain to the change in shape that occurs as a result. They're like two sides of the same coin, with stress causing strain and strain reflecting the amount and type of stress applied. It's important to note that the Earth's crust isn't a passive player in all this. It responds to these stresses, often in dramatic ways, by bending, breaking, or flowing. Different rocks respond in different ways, depending on factors such as temperature, pressure, rock type, and the rate at which the stress is applied. These forces not only shape the crust, but also lead to various types of failure, which we will discuss next. The Earth's crust is an intricate, ever-changing tapestry woven by the ceaseless interplay of tectonic forces, stress, and strain. So, stay tuned to unravel more about the fascinating world beneath our feet. When the forces within the Earth's crust become too intense, failures occur. But what are these failures, you ask? Well, let's explore some of them in detail. Imagine you're holding a piece of chalk. If you apply enough pressure, it will suddenly snap. This is brittle failure. In geological terms, brittle failure happens when rocks break or fracture due to intense stress. It's like the chalk, but on a much larger scale. This type of failure is commonly seen in the Earth's crust, where cooler temperatures and low pressures prevail. Now, instead of a piece of chalk, picture a ball of clay. If pressure is applied to it, the clay deforms but doesn't break. This is what we call ductile failure. Rocks experiencing ductile failure deform and change shape without cracking or fracturing. This happens deeper within the Earth, where higher temperatures and pressures allow rocks to bend and flow rather than break. Lastly, let's talk about elastic failure. Picture a rubber band. When you stretch it, it gets longer. If you let go, it snaps back to its original shape. However, if you stretch it too far, it breaks. This is akin to elastic failure in rocks. When stress is applied, rocks can deform elastically and return to their original shape once the stress is removed. But if the stress is too great, the rocks will reach a breaking point, leading to failure. Each type of failure is a result of the interplay between stress, strain, and the properties of rocks. The temperature, pressure, and the rock's composition all play a part in determining whether a rock will fail brittly, ductilely, or elastically. While these failures signify the Earth's dynamic nature, they also set the stage for various sliding phenomena. So as we delve deeper into the mysteries of our planet, remember every crack, crevice, or mountain range tells a story of the powerful forces at work beneath our feet. Sliding, a common phenomenon in geology, may seem straightforward, but there's more to it than meets the eye. Let's start with the Coulomb criterion. Named after Charles-Augustin de Coulomb, this criterion is used to predict the conditions under which a material might fail due to sliding. It considers the shear strength of the material, which is the resistance against deformation by sliding. The Coulomb criterion suggests that the shear strength is a combination of cohesion, the natural stickiness between particles, and friction, the resistance experienced when one body moves over another. Next, we have the Tresca criterion. Gustav Tresca proposed this criterion, which is particularly useful for understanding ductile materials like metals and rocks under high pressure. According to the Tresca criterion, failure occurs when the maximum shear stress within a material exceeds its yield strength. In simpler terms, it's like reaching the limit of how much you can stretch a rubber band before it snaps. Last but not least, we have the von Mises criterion, named after Richard von Mises. This criterion is a bit more complex as it takes into account the distortional or shape-changing energy within the material. According to the von Mises criterion, failure occurs when the distortional energy exceeds a certain limit. It's like inflating a balloon. The more air you pump in, the more the balloon distorts until it eventually pops. These sliding criteria provide a mathematical framework to understand the conditions under which rocks slide or deform. They also help in predicting landslides, a major geological hazard. By understanding the strength of the soil or rock and the stresses it's subjected to, we can estimate when and where a landslide might occur. Understanding these criteria not only helps in predicting landslides, but also unravels the mysteries of Earth's ever-changing face. Today, we embarked on a journey through the depths of the Earth, uncovering its secrets. We dived into the enigma of Earth's structure, unveiling the hidden layers and complexities beneath our feet. Our tale of tectonic forces took us through the colossal powers that shape our planet, creating mountains, valleys, and the very ground we stand on. We then unraveled the types of failure, shedding light on how the Earth's crust reacts to these immense forces. From brittle to ductile failures, we saw how the crust bends, breaks, and reshapes itself. This knowledge led us to decode the sliding criteria, understanding what triggers these movements and the role of factors such as stress, strain, and material properties. As we continue to decipher the language of the Earth, we unravel more about our planet's past, present, and future. Remember, every rock has a story to tell if we're willing to listen. Thanks for watching us share our videos, subscribe our YouTube channel, and press the bell icon and stay curious for new uploads.